What if the closest star to our sun harbors a planet where humans could one day settle? In 2016, astronomers discovered Proxima Centauri b, an exoplanet located just 4 light years away. Reaching this distant world isn't merely a fantasy, it's a challenge that modern science is beginning to tackle. Imagine embarking on a voyage spanning over 25 trillion miles. The spaceflight technology we currently possess, such as the ion propulsion used in deep space missions, is nowhere near sufficient for such an undertaking. However, within past blueprints and cutting-edge research lie the potential keys to interstellar travel. But distance is not the only hurdle to overcome. Today we'll explore this topic and examine whether humanity's next great leap could take us to Alpha Centauri. For centuries, the dream of interstellar exploration has captivated the human imagination. However, it wasn't until the 20th century that scientific progress began to catch up with science fiction. The journey towards space exploration took a significant leap forward in 1961, when Yuri Gagarin became the first human to orbit Earth, proving that people could survive and work beyond our planet. This breakthrough paved the way for the Apollo program, culminating in the historic 1969 moon landing. Neil Armstrong and Buzz Aldrin's first steps on the lunar surface were not just a triumph for humanity, they demonstrated our ability to reach and explore other celestial bodies. In the 1970s, the Voyager missions expanded our knowledge of the outer planets and the heliosphere. These probes, now traveling through interstellar space, carry golden records containing messages intended for any extraterrestrial intelligence that might one day encounter them. However, humanity is far from finished. Recent advancements in propulsion technology are crucial to making deep space travel feasible. Missions like NASA's Dawn spacecraft have demonstrated the efficiency of ion engines, which generate thrust by accelerating electrically charged particles. This method is far more fuel efficient than conventional chemical rockets, enabling long-duration missions. At the same time, our understanding of the cosmos has been revolutionized by the discovery of exoplanets, planets orbiting stars beyond our solar system. The first confirmed detection occurred in 1992, when astronomers found 2 rocky planets orbiting a pulsar. This shattered previous assumptions and fueled the search for other potentially habitable worlds. In 1995, the discovery of 51 Pegasi b, the first exoplanet detected around a sun-like star, further reinforced the idea that planets are abundant in the universe. This gas giant, located about 50 light years away, marked the beginning of an era of exoplanet discoveries that continues today. Among the most exciting finds is Proxima Centauri b, identified in 2016. This exoplanet orbits Proxima Centauri, the closest star to our sun, at a distance of just 4.24 light years. Situated within its star's habitable zone, Proxima Centauri b could have conditions suitable for liquid water, making it a prime candidate for future exploration and potential colonization. The discovery of this exoplanet was made using the radial velocity method, which detects small wobbles in a star's motion caused by the gravitational pull of an orbiting planet. To date, this method has led to the identification of thousands of exoplanets, bringing us closer to finding a world capable of supporting life. The feasibility of traveling between stars depends on our ability to develop highly efficient propulsion systems. While current spaceflight technology has made remarkable progress, it remains inadequate for interstellar journeys. Ion propulsion represents one of the most advanced space travel technologies available today. Unlike chemical rockets that generate thrust through combustion, ion engines use electricity to ionize a propellant, typically a xenon gas, and accelerate the charged particles to produce thrust. NASA's Dawn spacecraft, launched in 2007, showcased the potential of ion propulsion by exploring the asteroid belt, including the protoplanet Vesta and the dwarf planet Ceres. Ion engines enabled Dawn to enter and exit orbits in a way that would have been prohibitively expensive using traditional rockets. The key advantage of ion propulsion is its high fuel efficiency, allowing spacecraft to carry significantly less fuel for extended missions. However, the trade-off is that ion engines generate relatively low thrust, making them unsuitable for escaping Earth's gravity, where powerful propulsion is needed. Another significant achievement in modern space exploration was NASA's New Horizons probe, launched in 2006 to study Pluto and its moons. This mission provided humanity with the first close-up images of Pluto before continuing its journey into the Kuiper Belt, a region filled with icy remnants from the solar system's formation. New Horizons relied on a combination of chemical propulsion and gravitational assists to achieve its high velocity. A gravity assist from Jupiter helped accelerate the probe, allowing it to cover more than 3 billion miles in just 9 years. Despite the success, the limitations of current propulsion technology are evident. Even at speeds exceeding 36,000 miles per hour, New Horizons took nearly a decade to reach Pluto, highlighting the challenges of deep space travel. To traverse the vast distances between stars, we need propulsion systems capable of much greater speeds, sustained over long durations. One of the most ambitious propulsion concepts proposed is nuclear pulse propulsion. Originally conceived during the Cold War, this method involves detonating small nuclear explosions behind a spacecraft to generate thrust. First suggested by physicist Stanislaw Ulam in the 1950s, this idea was later developed into the Orion project. The principle behind nuclear pulse propulsion is relatively straightforward. Controlled nuclear explosions propel a spacecraft forward, with a large pusher plate absorbing the force. Calculations indicate that this method could achieve speeds up to 10% of the speed of light, significantly reducing travel time to nearby star systems such as Alpha Centauri. In recent years, the Breakthrough Starshot initiative has emerged as one of the most ambitious efforts to achieve interstellar travel within a human lifetime. This international project aims to send a probe to Alpha Centauri and potentially reach it within just 20 years. Breakthrough Starshot's key innovation is the use of a light sail, which would be propelled by an array of powerful ground-based lasers. Unlike conventional propulsion systems, this method does not require onboard fuel, making the spacecraft extremely lightweight and capable of reaching speeds up to 20% of the speed of light. However, the challenges of implementing this technology are substantial. The proposed laser array would require an optical power output of approximately 100 gigawatts, roughly 100 times the capacity of the world's largest battery. Additionally, keeping millions of laser beams precisely aligned to propel the light sail is a significant engineering challenge. To address this issue, researchers at the Australian National University have proposed using a laser-guided satellite to maintain accuracy throughout the journey. If successful, Breakthrough Starshot could transmit detailed images and scientific data from Alpha Centauri, offering unprecedented insights into our closest neighboring star system, while light sails and nuclear propulsion represent promising near-future technologies. Other theoretical concepts push the boundaries of physics. One such idea is the warp drive, inspired by Einstein's general theory of relativity. A warp engine would manipulate space-time itself, compressing space in front of the spacecraft and expanding it behind, allowing faster-than-light travel without violating known physical laws. Another radical proposal is the use of antimatter propulsion, which could theoretically achieve speeds approaching a significant fraction of the speed of light. However, the production and storage of antimatter remain formidable challenges due to its extreme cost and highly reactive nature. Another radical proposal is the use of antimatter propulsion, which could theoretically achieve speeds approaching a significant fraction of the speed of light. However, the production and storage of antimatter remain formidable challenges due to its extreme cost and highly reactive nature. The journey to the stars is filled with immense technical, logistical, and economic challenges. From radiation shielding to spacecraft durability and long-duration life support, numerous obstacles must be addressed before interstellar travel becomes a reality. Yet, the dream of exploring distant worlds persists. As humanity continues to push the frontiers of science and technology, the possibility of reaching Alpha Centauri may one day move from the realm of speculation to reality. The potential to sustain life continues to drive research efforts, and to support this pursuit, the European Southern Observatory has developed an advanced instrument specifically designed to search for exoplanets within the Alpha Centauri system. This cutting-edge tool, integrated into the Very Large Telescope in Chile, enhances our ability to detect Earth-like planets by refining radial velocity measurements with greater precision. The primary objective of this instrument is to identify planets similar in size to Earth by detecting the minuscule gravitational effects they exert on their host stars, with a particular focus on Alpha Centauri A and B, two sun-like stars in the system. The instrument seeks to discover additional planets that may exist within their habitable zones. Its improved sensitivity and resolution significantly increase the likelihood of identifying previously undetected worlds, offering a clearer understanding of the potential for habitable planets in our closest star system. The discovery of a habitable planet in Alpha Centauri would be an extraordinary breakthrough in our quest to understand how common life-supporting conditions are beyond our solar system. A potentially habitable planet so close to Earth would be an ideal candidate for future interstellar exploration, and even a possible target for human colonization. Recent advancements in the search for habitable exoplanets have yielded exciting findings. For instance, this past spring, astronomers identified an Earth-like exoplanet named LISA 12b, located just 40 light-years away. This planet, similar in size to Venus, orbits a red dwarf star and is estimated to have a surface temperature of approximately 107 degrees Fahrenheit. The discovery of such a world, which may possess an atmosphere, provides valuable insight into the conditions necessary for atmospheric retention and the presence of liquid water. NASA's Transiting Exoplanet Survey Satellite, TESS, played a crucial role in this discovery by detecting exoplanets through transit observations, watching for periodic dimming in a star's brightness as a planet crosses in front of it. During these transits, the star's light filters through the exoplanet's atmosphere, allowing scientists to analyze its composition using transmission spectroscopy. The significance of LISA 12b extends beyond its potential habitability. It serves as an important comparison point for understanding why Earth and Venus, despite their similarities, have evolved into vastly different environments. By studying LISA 12b, researchers hope to gain deeper insights into atmospheric retention and the evolutionary pathways of Earth-like planets orbiting cooler stars. An important focus since red dwarfs are the most common type of star in the Milky Way. LISA 12b is estimated to be roughly the size of Earth or slightly smaller, placing it in the same category as Venus within our solar system. Ongoing efforts to discover and study potentially habitable planets in Alpha Centauri and nearby star systems continue to evolve, with instruments such as the James Webb Space Telescope, JWST, playing a critical role in refining our understanding of planetary conditions conducive to life. Although humans may not be the first to explore these distant worlds, technological advancements allow us to send robotic probes as precursors to future missions. Intelligent robotic explorers and artificial intelligence, AI, are expected to play a fundamental role in interstellar exploration, as these systems can operate autonomously, executing complex tasks without direct human intervention, making them ideal for extended missions far beyond our solar system. One of the most intriguing concepts in this regard is the theoretical idea of von Neumann probes, self-replicating machines that could explore the galaxy by utilizing local materials to create copies of themselves. This self-replication process would exponentially increase the number of probes, allowing for widespread exploration and even the potential for colonization without requiring continuous resupply from Earth. For human space travel, concepts such as interstellar arcs and self-sustaining habitats present a visionary approach to settling distant star systems. These colossal spacecraft would serve as mobile space colonies, housing large populations and providing all necessary resources to sustain life on long-duration, multi-generational journeys. Equipped with advanced life support systems, agricultural facilities, and social infrastructure, these habitats could ensure the well-being of their inhabitants as they voyage across the cosmos. In conclusion, while current technology limits us to relatively modest space travel, these ambitious concepts offer a glimpse into a future where humanity may one day break free from the confines of our solar system. As technology progresses, what once seemed like science fiction could become reality, paving the way for humanity's expansion into the stars. The question of whether we are alone in the universe is as ancient as the starlight that has traveled for eons to reach us. Since the dawn of civilization, humans have gazed at the night sky in wonder, their imagination sparked by the distant twinkling of celestial bodies. Today, with the power of modern science and technology at our disposal, we continue to seek answers to this age-old mystery. However, our goal is not just to detect primitive life, but to uncover potential signals from civilizations that may share this vast cosmic stage with us. The Breakthrough Listen project is the most ambitious initiative dedicated to searching for signs of extraterrestrial intelligence. By pushing the boundaries of our technological capabilities, this project aims to detect technosignatures, signals that indicate the presence of advanced civilizations. Several scientific teams associated with Breakthrough Listen and other SETI search for extraterrestrial intelligence programs have already published studies that bring us closer to answering this fundamental question. Our pursuit of life beyond Earth follows two primary pathways: the search for biosignatures and the search for technosignatures. Each provides a distinct perspective on the possibility of life in the universe, guided by the principles of astrobiology and cutting-edge technology. Biosignatures are chemical indicators of life, offering potential clues about biological activity on distant planets. These markers are not just evidence of life, but reflections of the complex interactions between living organisms and their environments. Oxygen, ozone, methane, and carbon dioxide are among the most significant biosignatures. The James Webb Space Telescope, JWST, with its exceptional sensitivity to the infrared spectrum, is at the forefront of this search. Using transmission spectroscopy, JWST examines starlight as it passes through the atmospheres of exoplanets, identifying key molecular signatures that hint at possible life. This method provides valuable insights into atmospheric composition, climate, and potential habitability. While biosignatures suggest life in its simplest forms, technosignatures point toward advanced civilizations capable of manipulating their environment. These could range from artificial radio signals to massive space structures. Unlike biosignatures, which indicate the presence of life in any form, technosignatures suggest a leap in complexity, evidence of intelligence beyond Earth. Projects like Breakthrough Listen leverage networks of radio telescopes to scan the cosmos for potential extraterrestrial transmissions. By analyzing anomalies in the natural cosmic radio background, scientists aim to detect signals that may indicate deliberate attempts at interstellar communication. As we continue to refine our methods for detecting biosignatures and technosignatures, our understanding of life's potential beyond Earth expands. Whether through robotic exploration, AI-driven probes, or one day even human interstellar travel, the search for extraterrestrial life remains one of humanity's greatest endeavors. As technology advances, the prospect of discovering life, or even civilizations beyond Earth, grows increasingly tangible, bringing us closer to answering one of the most profound questions ever asked. Are we alone in the universe? Perhaps comparable to, or even surpassing our own, technosignatures differ from biosignatures in a fundamental way. While biosignatures merely suggest the presence of life, technosignatures reveal the capacity of civilizations to transform their environment on a massive scale, communicate across the cosmos, and harness energy in ways we are only beginning to comprehend. These indicators encompass a vast spectrum of signals and structures, ranging from radio waves unintentionally emitted by planetary communication systems to deliberate interstellar beacons. They include massive energy collecting constructs, such as Dyson spheres, and even the faint glow of city lights on the night side of distant exoplanets. If detected, these technosignatures would not only confirm the existence of life, but also provide profound insights into the technological capabilities of extraterrestrial civilizations. Our own planet is a prime example of a world teeming with technosignatures. Every radio transmission, satellite, and the piece of space debris orbiting Earth generates a symphony of signals that, to a distant observer, unmistakably indicate the presence of an advanced civilization. The very fabric of our daily lives, from global communication networks to deep space probes, produces a cascade of emissions that travel into space, making our presence known to any who might be listening. But why are technosignatures a more precise method for identifying advanced civilizations? The answer lies in their specificity and the deliberate or highly structured nature of the signals and structures they represent. While biosignatures can emerge from simple microbial life to complex ecosystems, technosignatures unmistakably indicate a level of technological advancement and intent. Detecting such a signature would not only confirm the existence of extraterrestrial life, but also demonstrate that this life has reached a cognitive and technological threshold, engaging in activities that leave a lasting imprint on the cosmos. Launched in 2016, Breakthrough Listen is an ambitious initiative dedicated to scanning the universe for signs of technologically advanced civilizations. It represents one of the most comprehensive searches for alien technosignatures ever undertaken, leveraging cutting-edge technology in an unprecedented scope. The project employs some of the most powerful radio telescopes on Earth, such as the Green Bank Telescope and the Parkes Observatory. These enormous instruments, attuned to the faintest whispers of the cosmos, are capable of detecting a broad range of signals, from subtle radio emissions originating from distant stars to potential transmissions of extraterrestrial origin. At the core of Breakthrough Listen's mission is the goal of detecting technosignatures, signals that by their very nature could only be generated through technological means. These may include narrowband radio waves that stand out from cosmic background noise, or highly focused laser pulses cutting through the vast expanse of space. Initially, the project concentrated its efforts on the Milky Way for strategic reasons, starting the search within our cosmic neighborhood, where such signals would likely be strongest and easiest to detect. With its billions of stars, the Milky Way offers a promising landscape for this endeavor, as each star could potentially host planets, each of which might cradle life, either as we know it or in entirely unfamiliar forms. The challenge of searching for technosignatures is akin to identifying a single whispered word in the midst of a bustling metropolis. A galaxy containing roughly 100 billion stars can easily conceal the signals of intelligent civilizations. The sheer number of potential targets, combined with a complex array of cosmic phenomena that can obscure or mimic artificial signals, makes the task monumental. Adding to the difficulty, our technological limitations and finite resources restrict the number of stars we can monitor at any given time. Vast distances weaken signals over time, while natural cosmic phenomena, such as emissions from pulsars and nebulae, further complicate the search. Faced with these challenges, astronomers have extended their focus beyond the Milky Way to explore the wider universe. By observing entire galaxies as unified systems, each containing billions of stars, they aim to detect the collective technosignatures of highly advanced civilizations. This extragalactic approach is built on the premise that sufficiently advanced beings might develop technologies capable of influencing entire galaxies, from constructing mega structures like Dyson spheres to harnessing the immense power of supermassive black holes. Such grand-scale engineering projects could produce detectable technosignatures even from vast intergalactic distances. However, transitioning to extragalactic studies presents new obstacles, such as greater distances that weaken signals, the need for more sensitive instruments, and more sophisticated data analysis techniques. Despite these difficulties, every observed galaxy and analyzed dataset brings us closer to answering the ultimate question: are we alone in the universe, or are we part of a vast interconnected galactic community? In 2023, astronomer Carmen Choza and her team embarked on one of the most ambitious extragalactic technosignature searches ever conducted, utilizing the Robert C. Byrd Green Bank telescope. Over the course of 5 years, they meticulously examined the cores of 97 nearby galaxies, scanning 4 frequency bands between 1 and 11 GHz. Their objective was to identify signals indicative of civilizations capable of harnessing energy on the scale of a Kardashev Type II civilization. A key aspect of this study was the implementation of the Turbo SETI pipeline, a sophisticated tool designed to detect Doppler drift, a telltale sign of an artificial transmission. To combat the persistent challenge of radio frequency interference, RFI, which often mimics extraterrestrial signals, the team employed an on-source, off-source observation cadence. This technique involved alternating between a target galaxy, on-source, and a nearby empty region of space, off-source, 3 times for each observation, since terrestrial interference and background noise appear in both on-source and off-source readings, whereas genuine astronomical signals should only manifest in the target data. This approach helped distinguish real signals from interference, improving the reliability of their findings. Despite their meticulous methodology and advanced technology, the study encountered significant challenges, primarily due to RFI contamination. To mitigate this issue, the team employed innovative filtering strategies, including signal injection and recovery tests, to differentiate between Earth-based and potential extraterrestrial sources. This highlighted the immense difficulty of identifying technosignatures, as any signals originating from outside our galaxy would need to be extraordinarily powerful to stand out from the surrounding cosmic noise. The exhaustive search yielded an initial 634,313 potential detections, after applying advanced computational algorithms for further refinement. This number was reduced to 1,519 events of particular interest. Each of these was then carefully scrutinized by researchers who attempted to distinguish extraterrestrial signals from terrestrial interference. Ultimately, all 1,519 events were determined to be linked to human-generated sources or natural cosmic phenomena. Although no definitive technosignatures were found, Choza and her team's work provides a critical foundation for future research. Machine learning and evolving analytical techniques promise to refine our ability to uncover signals that may have previously been overlooked or misinterpreted as noise. As SETI research continues to evolve, driven by technological innovation, our ability to explore the cosmos grows ever more sophisticated, inching us closer to potentially discovering intelligent life beyond Earth. Over time, improved observational techniques have led to the widely accepted perception of Neptune's deep blue hue. But what truly led to this understanding? The answer lies in a detailed study titled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This research, led by Patrick G.J. Irwin from Oxford University alongside a team of specialists, aimed to uncover the mysteries behind Uranus's seasonal color shifts. However, their work unexpectedly shed new light on Neptune's true appearance, challenging long-standing assumptions. The researchers meticulously examined an extensive collection of data from L'Observatoire, spanning over 6 decades, complemented by observations from the Hubble Space Telescope. This thorough analysis provided a comprehensive depiction of Uranus's average color and photometric magnitude, highlighting the intricate relationship between its seasonal variations. A key aspect of this study was the investigation into Uranus's reflectivity and methane concentration. The team discovered a complex correlation between the lower methane levels at polar latitudes and the differing reflectivity of atmospheric aerosol particles. The presence of methane ice particles added another layer of complexity to their findings, reshaping our understanding of Uranus's atmospheric properties. At the same time, the study facilitated an intriguing comparison with Neptune. Contrary to popular belief, the contrast in blue tones between Neptune and Uranus was less dramatic than previously assumed. This revelation emerged from a critical reassessment of Neptune's color, dispelling the long-held notion of an intensely deep blue shade. To arrive at these conclusions, the researchers employed a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic techniques. They transformed observed reflectance spectra into radiance spectra, and then into tristimulus values, simulating how the planet's colors would appear to the human eye. This methodology bridged the gap between raw data and visual perception, offering a clearer representation of Neptune's true appearance. The use of advanced telescopes like Hubble and the Very Large Telescope, VLT, was instrumental in this breakthrough. These cutting-edge instruments allowed the team to reanalyze and refine their understanding of both Uranus's and Neptune's colors with unparalleled precision. Exploring Neptune's atmospheric conditions reveals a world of extreme weather, starkly contrasting with the relative calmness of its neighbor Uranus. Neptune's atmosphere is a turbulent and ever-changing system, featuring some of the most intense meteorological activity in the solar system. One of its most remarkable features is the presence of massive storms, the most famous of which is the Great Dark Spot. First observed by the Voyager 2 spacecraft in 1989, this colossal storm, reminiscent of Jupiter's Great Red Spot, showcases the violent nature of Neptune's climate. These vast, rotating storms are fueled by the fastest winds in the solar system, which can reach speeds of up to 1,300 miles per hour, 2,100 kilometers per hour. However, the exact mechanisms driving these extreme winds remain a mystery, raising questions about their origins and energy sources. In contrast, Uranus presents a much more tranquil atmosphere. Despite being composed of hydrogen, helium, and methane, similar to Neptune, it lacks the same dramatic storms and violent winds. This striking difference in atmospheric activity between the two ice giants remains one of the great enigmas of planetary science. Another fascinating aspect of Neptune's atmosphere is the existence of mysterious hotspots, where temperatures soar to approximately 750 Kelvin, 477 degrees Celsius, or 890 degrees Fahrenheit. These warm regions are puzzling, given Neptune's vast distance from the Sun. Scientists hypothesize that internal processes such as auroras or magnetic reconnection in the planet's plasma layers might be responsible. However, the exact source of this heat remains unknown, prompting ongoing research into Neptune's internal dynamics. Beyond Neptune's turbulent atmosphere lies a celestial realm of moons and rings, where one moon, in particular, stands out, Triton. As Neptune's largest and most enigmatic moon, Triton exhibits remarkable seasonal variations in atmospheric phenomena. What makes Triton truly unique is its retrograde orbit, meaning it moves in the opposite direction of Neptune's rotation. This unusual motion suggests that Triton was not originally part of Neptune's system, but was instead captured by the planet's gravity. Unlike most other moons in the solar system, Triton's surface is geologically young and active, characterized by nitrogen ice and dark streaks that indicate geysers spewing nitrogen gas into space. Triton's thin atmosphere, which changes in thickness with the seasons, presents a compelling case for extraterrestrial meteorological studies. Observations from the European Southern Observatory's VLT have shown that Triton's southern hemisphere is currently experiencing its summer phase. Despite its great distance from the Sun, Triton undergoes significant atmospheric shifts due to seasonal warming, which causes frozen nitrogen, methane, and carbon monoxide on its surface to sublimate into gas. With Neptune's orbit around the Sun spanning 165 Earth years, Triton's seasons last for decades. The most recent southern summer solstice occurred in 2000, marking a peak in its seasonal changes. The discovery of carbon monoxide and methane in Triton's atmosphere has further advanced our understanding of this intriguing moon, necessitating updates to climate and atmospheric models. The interplay of nitrogen, methane, and carbon monoxide not only shapes Triton's atmosphere, but also offers clues about its geological and climatic evolution. Triton is not alone. Neptune is accompanied by a collection of smaller moons, each contributing valuable insights into the complex gravitational interactions and environmental conditions of this distant world. Shifting our focus from Neptune's moons to its rings, we uncover another layer of the planet's mystique. Neptune's rings, composed of dust and ice particles, appear faint yet captivating. These structures serve as remnants of a dynamic past, possibly formed from the debris of moons destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are intricately linked to Neptune's atmospheric properties. The delicate hues of the rings, influenced by light scattering in the planet's atmosphere, subtly contribute to Neptune's overall coloration. In 2022, the James Webb Space Telescope captured the clearest images of Neptune's rings in over 3 decades. These high-resolution observations provided an unprecedented look at the rings, some of which had not been clearly detected since Voyager 2's flyby in 1989. Webb's advanced infrared imaging capabilities revealed intricate details previously hidden in the darkness of space, offering new insights into their structure and behavior. Unlike the gas giants Jupiter and Saturn, Neptune is classified as an ice giant, meaning it contains a higher proportion of elements heavier than hydrogen and helium. This distinction is also reflected in its color. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight, creating bright streaks and patches. Interestingly, in infrared images captured by Webb's near-infrared camera, NIRCam, Neptune does not appear blue. Instead, it takes on a luminous white glow, highlighting the influence of atmospheric methane absorption. A striking feature in these images is Triton, appearing as a dazzling point of light, surrounded by diffraction spikes. These spikes are not physical structures, but rather optical artifacts resulting from the telescope's design. The way light interacts with the telescope's mirrors and components creates these star-like patterns, a common phenomenon in space imaging. The study of Neptune's rings, especially in infrared, provides invaluable information about the planet's atmospheric conditions and internal composition. The interaction between the rings and Neptune's atmosphere, particularly with methane ice clouds, sheds light on the planet's climatic and environmental processes. The bright equatorial band visible in infrared hints at Neptune's global atmospheric circulation, a crucial factor in driving its powerful winds and storms. As our exploration of Neptune concludes, we reflect on how these discoveries have reshaped planetary science and deepened our understanding of ice giants and exoplanets beyond our solar system. Once seen as a distant, deep blue dot, Neptune now stands as a dynamic and ever-evolving world. Its true color, atmospheric phenomena, rings and moons appear to provide a foundation for studying similar planets in other star systems, broadening our knowledge of the universe. The knowledge gained from Neptune will aid astronomers in unlocking the secrets of these remote worlds, deepening our understanding of the universe as we continue to explore the cosmos. Neptune serves as a reminder of the endless possibilities for discovery, inspiring us to keep searching, questioning, and unraveling the universe's many mysteries. The moon has long been a symbol of mystery and wonder. Yet, beyond its luminous beauty and the folklore woven around it, the moon holds secrets that have eluded us for centuries. Among its most enigmatic regions is the moon's south pole, a place of perpetual darkness and extreme cold, untouched and unexplored by previous missions. This is the story of Chandrayaan-3, India's bold venture into uncharted territory. Traveling more than 238,000 miles, this mission was not only a journey of distance, but of discovery. Its objective: to probe the mysteries of the moon's south pole, a terrain so rugged and cratered that navigating it is akin to traversing a maze of obstacles. In this alien landscape, Chandrayaan-3 sought answers to long-standing scientific questions. What lies beneath the surface of the shadowed region? Do seismic tremors shake the silent world? And most intriguingly, does water, the essence of life, exist here in frozen form? As Chandrayaan-3 set off beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. The mission's primary goal was clear but formidable: achieving a soft landing near the moon's south pole, an achievement never before accomplished. From the bustling Mission Control Center of the Indian Space Research Organization, ISRO, a dedicated team of scientists and engineers steered this ambitious endeavor. Their expertise was crucial in guiding Chandrayaan-3 through the challenges of lunar orbit insertion and descent. The moon's south pole is unlike any other landscape. Its surface is a mosaic of craters and towering peaks, many cast in permanent shadow. The challenge wasn't just landing, it was landing safely in an area where steep slopes and treacherous terrain posed significant risks. As the Vikram lander separated from the orbiter, it began its descent, guided by advanced sensors and precision engines. Picture a spacecraft autonomously navigating a labyrinth of craters and boulders, searching for a stable landing site. As it made its final approach, the tension in mission control was palpable, each second critical, every maneuver a testament to human ingenuity and technological mastery. Then, with a gentle thud, Vikram landed, marking a historic moment, not just for India, but for lunar exploration as a whole. In the silent expanse of the moon's south pole, Chandrayaan-3 commenced its mission of discovery. Following this groundbreaking landing, a new chapter in lunar exploration unfolded. The mission aimed to study the moon's unique characteristics, particularly its tenuous exosphere and ionosphere, and to establish the extent of temperature variations just below its surface. The moon's exosphere, a thin veil of gases surrounding it, offers vital clues about its past and present. Unlike Earth's dense atmosphere, the moon's exosphere is so sparse that it resembles a near vacuum. Instruments on board Chandrayaan-3, developed using cutting-edge technology, were designed to measure the density and composition of this elusive layer. Beyond the exosphere, the mission also examined the moon's ionosphere, a layer formed as solar radiation ionizes atoms in the thin lunar atmosphere. This region plays a crucial role in lunar communication and navigation. Chandrayaan-3's measurements provided unprecedented insights into the ionosphere's behavior, invaluable for future lunar missions and potential human habitation. Another fascinating objective was studying temperature fluctuations beneath the lunar surface. Using the Chandra's Surface Thermophysical Experiment, CHASTE, a temperature probe embedded in the lunar regolith mapped the thermal profile of the moon's soil. The findings revealed stark contrasts. Surface temperatures soared to 140 degrees Fahrenheit during lunar daytime, while just 8 centimeters below, they plummeted to 14 degrees Fahrenheit. This suggested that lunar regolith could act as a natural thermal insulator, offering potential protection for future astronauts against extreme temperatures and radiation. These investigations weren't just scientific pursuits, they laid the foundation for future space exploration. Data from Chandrayaan-3 on the lunar exosphere, ionosphere, and subsurface temperatures provided essential insights into the moon's environment and its ability to support human life. Standing amidst this alien landscape, Chandrayaan-3 was poised to observe a phenomenon unseen for over half a century: a lunar earthquake. The mission succeeded in shedding light on one of the moon's most enigmatic and least understood processes. The Instrument for Lunar Seismic Activity, IELSA, a highly sensitive seismic detector, picked up what appeared to be a lunar quake, a groundbreaking discovery since the last recorded observations during the Apollo missions in the 1970s. Unlike Earth, where seismic activity results mainly from tectonic plate movements, the moon, lacking such plates, experiences tremors for different reasons. These tremors can last significantly longer than earthquakes, sometimes up to an hour. Scientists propose multiple possible causes: meteoroid impacts sending shockwaves through the moon's crust, gravitational stresses from Earth's tidal forces, or extreme temperature shifts, causing the lunar surface to expand and contract. These lunar quakes are not just surface-level events. They provide a glimpse into the moon's interior. By analyzing seismic waves, scientists can infer the structure and composition of the moon's subsurface, much like performing a sonogram on the lunar interior. This information is invaluable for understanding the moon's formation and evolution. Chandrayaan-3's discoveries extended beyond seismic activity. Among its most intriguing finds was sulfur, an element whose presence on the moon had remained a mystery. The Laser-Induced Breakdown Spectroscope, ELIBS, aboard the rover detected sulfur by vaporizing tiny soil samples and analyzing the emitted light. On Earth, sulfur is often linked to volcanic activity, raising questions about whether similar processes once shaped the moon's surface. Another critical objective was the search for water ice, a resource crucial for future lunar missions. While Chandrayaan-3 did not find direct evidence of surface ice, this absence is not a conclusion but a clue, leading scientists to consider alternative theories. One possibility is that water vapor migrates to permanently shadowed craters, freezing into ice deposits beyond immediate detection. Beyond sulfur, Chandrayaan-3's LIBS instrument provided the first ever in situ elemental analysis of the moon's south pole. It identified aluminum, calcium, iron, chromium, and titanium, each element offering insights into the moon's complex geologic history. Further measurements revealed silicon and oxygen, essential components in understanding lunar formation. Ongoing studies continued the search for hydrogen, a key element in the hunt for water. These findings highlight the moon's geological diversity and set the stage for future exploration. Chandrayaan-3's mission was not just about uncovering the moon's past, but preparing for humanity's future beyond Earth. With Chandrayaan-3's success, new missions are on the horizon. The Lunar Polar Exploration Mission, LUPEX, a joint initiative between ISRO and the Japan Aerospace Exploration Agency, JAXA, aims to build upon Chandrayaan-3's legacy. Slated for launch no earlier than 2026, LUPEX will deploy a robotic lander and rover to further investigate the moon's south pole, with a key focus on water ice detection. Meanwhile, ISRO's Chandrayaan-4, planned for 2028, will attempt a groundbreaking lunar sample return. This complex mission will involve collecting lunar soil, docking in orbit, and returning samples to Earth, offering invaluable insights into the moon's composition and history. Chandrayaan-3's groundbreaking discoveries, from sulfur detection to lunar seismic activity, have unlocked new dimensions of our celestial neighbor. These findings are crucial stepping stones in lunar science, paving the way for future exploration and potential human settlement. Looking ahead, the future of lunar exploration is bright. Missions like LUPEX and Chandrayaan-4, building on past achievements, will continue pushing the boundaries of our understanding. India is not merely participating in this new era of space exploration, it is pioneering it. Beyond the moon, other mysteries beckon, among them Kepler-22b, a planet orbiting in the habitable zone of its star, captures our imagination. Discovered by NASA's Kepler Space Telescope, this distant world invites us to question the very nature of life beyond Earth. Kepler-22b is more than just a planet. It is a reminder of the endless frontiers that await us. As we journey deeper into the cosmos, our search for habitable worlds continues, opening new doors to possibilities beyond our own. In the vast array of cosmic interactions between planets and stars, there exists a delicate and narrow region, a zone where conditions are just right for the hope of life, as we know it, to persist in the darkness. This region, called the habitable zone, is a cradle for potential life, a sanctuary where water can exist in its liquid form, not boiling under the intense heat of a star, nor freezing in the cold vacuum of space. Imagine a world strikingly similar to Earth, nestled within this life-supporting zone, where the heat from the star is neither too extreme nor too weak, casting the planet in a gentle light. This is where Kepler-22b orbits quietly within the habitable zone of its star, making it a prime candidate in the search for Earth-like conditions and the potential for life beyond our solar system. Just as Earth flourishes in the Sun's habitable zone, Kepler-22b enjoys a similar privilege, orbiting at a distance where temperatures allow the existence of lakes, rivers, and oceans. The presence of liquid water, a universal solvent, is crucial as it is within water that the chemistry of life unfolds, providing the medium for everything from simple bacteria to complex plants and animals. However, water in its liquid state is just one of many essential factors needed to sustain life. What have we discovered from studying this distant world, and does it really hold a possibility of supporting humans? As we dive deeper into the mysteries of Kepler-22b, we embark on a journey of discovery, piecing together the puzzle of this faraway planet through the lens of our own Earth. With each new observation, scientists are getting closer to understanding the fundamental nature of this far-off world, from its size and composition to the very air that surrounds it. These factors will help reveal whether Kepler-22b holds the basic components needed to support life, or is at the forefront of the search for life is the crucial factor of liquid water, the foundation of all known biological processes. Kepler-22b, positioned perfectly in the habitable zone of its star, receives a steady flow of energy that suggests temperatures might be favorable for liquid water. But while the presence of water is promising, the composition and behavior of Kepler-22b's atmosphere remain unknown. The planet's atmosphere is the key determinant of environmental conditions, influencing temperature and surface pressure. If Kepler-22b's atmosphere is similar to Earth's, rich in nitrogen, with the necessary amount of oxygen and trace gases, it could mean a temperate climate and stable water cycles, just like those that sustain life on Earth. However, given the vast range of possible atmospheric conditions, uncertainty remains due to current technological limitations in directly observing exoplanet atmospheres. If Kepler-22b's atmosphere were dense and carbon dioxide dominated like Venus, it could trigger a powerful greenhouse effect, making the planet too hot for life. In contrast, a thin atmosphere lacking greenhouse gases could leave the planet frozen and exposed to harmful cosmic radiation. The estimated equilibrium temperature of Kepler-22b, around 72 degrees Fahrenheit, under Earth-like atmospheric conditions, suggests the potential for an environment suitable for Earth-like life. But if a Venus-like greenhouse effect were in place, temperatures could soar to a scorching 860 degrees Fahrenheit, likely preventing life as we know it. The elemental ingredients for life extend beyond water and atmosphere. Life, as we understand it, relies on a variety of chemical elements, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. While Kepler-22b's star is a G-type star with a similar composition to our Sun, the protoplanetary disks surrounding it influence the distribution of materials which would ultimately shape the planet's composition. Once formed, the planet's makeup could be altered through differentiation and geological processes, such as volcanic activity and plate tectonics. While direct measurements of Kepler-22b's chemical composition are out of reach, its location in the habitable zone suggests that the essential building blocks for life may be present. The last essential ingredient for life is energy, and Kepler-22b's position in the habitable zone ensures a constant supply from its host star. This energy, which powers photosynthesis on Earth, could drive the fundamental biological processes necessary for life. Although the true nature of Kepler-22b remains shrouded in mystery, its location makes it a tantalizing beacon of possibility, a world where the basic elements for life could converge. As we continue to explore distant worlds like Kepler-22b, the search for extraterrestrial life remains a fundamental part of our celestial explorations. With advanced instruments like the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the Extremely Large Telescope, we are edging closer to uncovering the secrets of these far-off planets. Through these technologies, scientists hope to analyze the atmospheres of exoplanets, looking for signatures of molecules that could indicate the presence of life. In the end, the quest for life beyond Earth is not just a scientific endeavor, but a profound exploration of our place in the cosmos. As we peer into the depths of space, we continue to push the boundaries of our understanding and redefine our place in the universe. The detection of sulfates in Martian formation suggests that water interacted with the planet's soil, leading to the deposition of minerals. The varying sulfate levels, along with patterns of mud cracks, create a picture of a planet where water levels fluctuated, fostering conditions that could have supported chemical reactions potentially related to the origins of life. The search for water on Mars is crucial in understanding the planet's climate, geological history, and potential for habitability. Recent discoveries have significantly altered our understanding of the red planet by revealing water in different forms and locations. Mars has many geological features pointing to past water activity. Ancient lake beds, river valleys, and outflow channels reveal that water once flowed freely across the Martian surface, suggesting that the planet had a warmer, wetter climate capable of supporting liquid water. The sedimentary layers and mineral deposits in these ancient areas further support the idea that water was active on Mars for extended periods, possibly for thousands or even millions of years. One groundbreaking discovery is the presence of water ice near the Martian equator. Previously, ice was thought to be confined to the polar regions, but radar surveys and analyses have uncovered ice deposits at lower latitudes, including near the equator. This challenges earlier beliefs about Mars' climate, and suggests that water ice is more widespread across the planet than once thought. The discovery of equatorial ice deposits hints at a more complex water cycle on Mars, possibly indicating a climate similar to Earth's in the past. However, this doesn't necessarily imply that Mars supported life, as drastic climate changes would make the long-term development of life highly unlikely. Despite the lack of conclusive evidence for life on Mars, the presence of water in various forms remains significant, offering a minimal possibility of past biological activity. These water ice deposits could also be an invaluable resource for future human exploration, providing water for drinking, agriculture, and fuel production. Mars's mineralogical landscape is strikingly different from Earth's. Earth boasts over 6,000 minerals, reflecting its dynamic geological processes and the complex interaction between its biosphere and geosphere. In contrast, after 50 years of research, only 161 minerals have been identified on Mars, which not only highlights the mineral diversity gap, but also suggests differences in geological activity and history between the two planets. The limited mineral diversity on Mars raises concerns about the planet's ability to support life, as diverse minerals are essential for the development of complex organic molecules. Mars's geological past may have been more monotonous compared to Earth, but recent seismic data has revealed interesting findings. The InSight mission, for instance, detected what is believed to be the largest earthquake ever recorded on Mars, lasting about 6 hours. This event, with a magnitude of 4.7, hints at significant geological activity beneath the Martian surface, even though Mars lacks plate tectonics. The cause of these earthquakes may stem from internal stresses or processes not yet fully understood. Volcanic activity on Mars, both past and present, has shaped its surface. Studies have identified at least 40 volcanic events, some as recent as a few million years ago. The discovery of unusual polygonal structures beneath the surface suggests thermal contraction and expansion, indicating a history of volcanic activity. The Noctis Labyrinthus region, near the Tharsis Plateau, home to Olympus Mons, the largest volcano in the solar system, further demonstrates Mars' volcanic past, with deep valleys and canyons formed by stretching and bending of the Martian crust. The study of Mars' volcanic history provides crucial insights into its past climate, which may have been warmer and wetter, supporting liquid water on the surface. Understanding these processes could also help in future research, as regions with volcanic activity might hold clues to the planet's habitability and resource availability. Recent technological advancements, such as the Mars Oxygen SRU experiment, MOXIE, have demonstrated the potential for producing oxygen on Mars. Installed on NASA's Perseverance rover, MOXIE efficiently converts the Martian atmosphere's carbon dioxide into oxygen, proving a key technological breakthrough for future human missions to Mars. By producing oxygen from CO2, MOXIE reduces dependence on Earth for essential life support resources and could eventually help sustain larger crews and permanent settlements on Mars. In addition to the rover, the Perseverance mission included the Ingenuity helicopter, which exceeded its initial mission parameters. Originally designed for a brief technology demonstration, Ingenuity has completed over 70 flights, proving its resilience in the harsh Martian environment. This achievement opens the door for future aerial exploration on Mars, including tasks like sample retrieval. However, the mission to return Martian samples to Earth remains a monumental challenge. With an estimated cost of up to $11 billion, the task involves multiple spacecraft, precise robotics, and significant financial resources. This highlights the complex and expensive nature of space exploration and raises questions about the allocation of resources. International cooperation in Mars exploration presents both opportunities and challenges. While collaboration can pool resources and enhance scientific outcomes, political and logistical considerations may complicate the process, as seen with the International Space Station's successes and constraints. As Mars becomes a focal point for exploration and potential colonization, the growing issue of space debris in Martian orbit poses a significant challenge. Preventing the accumulation of debris and developing technologies to manage it will be crucial for the safety and sustainability of future missions. While Mars colonization is increasingly plausible due to technological advancements, it also raises ethical, social, and environmental questions. The responsibility of expanding humanity's presence to another planet involves ensuring that lessons learned from Earth are applied to Mars. The future of Mars exploration holds tremendous promise, but it will require overcoming various technical, financial, and ethical challenges. The collective effort of the global community will be key to turning the dream of Mars exploration into reality. Supernovae, powerful cosmic explosions that shape galaxies, are integral to understanding the universe. These events occur at the end of massive stars' life cycles, ejecting elements that form new stars, planets, and life. The study of supernovae, especially through imaging, helps astronomers learn about their structure and the elements they disperse. The star Betelgeuse, a red supergiant, has recently drawn attention due to its fluctuating brightness, sparking speculation about an imminent supernova explosion. Early observations of a dust cloud around the star suggested a precursor, but later studies indicated it was a natural part of the star's life cycle. Betelgeuse's life cycle, from a massive hydrogen-burning star to a red supergiant nearing the end of its life, offers insight into the behavior of supernovae. The star's size accelerates its nuclear fusion, leading to rapid fuel depletion and instability, unlike our Sun, which burns fuel at a slower, more stable rate. Betelgeuse's eventual explosion will be a significant event, reshaping our understanding of stellar evolution. As Betelgeuse aged, it underwent successive stages of nuclear fusion, gradually burning off elements heavier than hydrogen. This process caused its internal pressure to build, leading the star to expand, transforming it from a main sequence star into a red supergiant. This phase is marked by Betelgeuse's immense size and fluctuating brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations suggest that Betelgeuse could be nearing the end of its life. In 2019, its dimming followed by an unexpected brightening led scientists to hypothesize that it might be approaching the final stages of its existence. These brightness fluctuations are thought to be connected to internal changes, possibly signaling the beginning of core collapse. Betelgeuse's pulsations, with cycles ranging from 185 to 2,200 days, were studied to understand its internal dynamics. The longest cycle, lasting 2,200 days, is particularly interesting as it could indicate the star's fundamental pulsation mode, suggesting it is in an advanced stage of its evolution. Recent observations and telescope findings also hint that Betelgeuse may be entering the carbon combustion phase that precedes a supernova. However, the nuclear processes that determine when a star's life ends are intricate. In massive stars like Betelgeuse, nuclear fusion converts hydrogen into helium, releasing massive energy. As the star ages, it fuses heavier elements, forming layers around the core. Eventually, the core fills with iron, which cannot generate energy through fusion. This leads to a gravitational collapse. As the core collapses under intense gravitational forces, temperatures soar to billions of degrees, triggering a catastrophic reaction. The core inflates before exploding in a shockwave that disintegrates the star. A supernova releases an enormous amount of energy, momentarily outshining an entire galaxy. The dynamics of this event involve complex interactions between nuclear collapse, gravitational forces, and intense heating. The shockwave generated by the core's collapse ejects the outer layers of the star into space, Supernovae have been observed by ancient astronomers, who often referred to them as guest stars. These rare phenomena continue to be studied, particularly when they lead to events like gamma ray bursts, GRBS. GRBs are intense bursts of gamma radiation usually linked to the collapse of massive stars or the merger of neutron stars. These bursts are some of the universe's most energetic events, releasing more energy in a few seconds than the Sun will over its entire 10 billion year lifespan. In October 2022, the discovery of the BOAT GRB, GRB 22109A, the brightest gamma ray burst ever recorded, marked a milestone in GRB observations. The event, originating from a galaxy 2.4 billion light years away, lasted about 7 minutes, much longer than typical GRBs. It was so powerful that it temporarily disrupted Earth's ionosphere, affecting radio communications and altering atmospheric ionization. While supernovae and GRBs are linked in some cases, especially when the core of a rapidly rotating star with a strong magnetic field collapses, scientists are still working to understand the mechanisms behind these cosmic events. The BOATGRB was also instrumental in providing insight into the formation of heavy elements. Initially, scientists hoped it could reveal how elements heavier than iron form, which typically occurs during supernova explosions or neutron star mergers. However, further research showed that GRBs do not produce these elements, adding to the mystery of these cosmic phenomena. To study this event, astronomers use various observational tools, including the James Webb Space Telescope. The initial brightness of the burst hindered observations, but after a few months it became possible to detect a relatively undetectable supernova remnant, which was unexpected considering the power of the GRB. The BOAT GRB also revealed that the gamma ray burst was highly focused, with narrow jets directed toward Earth, likely caused by a rapidly rotating star with a strong magnetic field. These jets contributed to the burst's exceptional brightness. Despite the insights gained from the BOATGRB, scientists are still exploring the mysteries surrounding Betelgeuse. Recent studies suggest that its cycles of dimming and brightening are part of its natural behavior as a variable star. Unlike our Sun, Betelgeuse is an explosive, low-density plasma cloud that changes shape frequently. Simulations have shown that its brightness cycles occur approximately every 400 days, with a longer cycle of around 2,000 days. In 2020, Betelgeuse experienced a significant dimming event that initially led to speculation that it might be on the verge of a supernova. However, observations from multiple telescopes have revealed that this was due to the formation of a large dust cloud obscuring the star. The star had undergone internal changes that caused material to separate, forming a gas cloud. This, along with shockwaves observed in 2018 and 2019, prove that Betelgeuse's behavior is part of its natural life cycle and not necessarily indicative of an imminent supernova. Betelgeuse also has an unusually high rotation rate, rotating at about 3 meters per second, unlike typical red supergiants, which rotate slowly. Initially, this led researchers to think it might have been part of a binary system that collided. However, recent research suggests that this rotation could be caused by fast-moving convective cells within the star, not binary interaction. In conclusion, while Betelgeuse is nearing the end of its life as a red supergiant, it is unlikely to explode as a supernova in our lifetime. The star's current state is more consistent with a variable red supergiant, rather than a star on the cusp of a supernova explosion. The potential effects of a supernova explosion on Earth remain a subject of speculation. While a supernova within a few light years could affect Earth's atmosphere, a supernova at a much greater distance, like the BOAT GRB, can still have significant impacts, such as ionospheric disruptions and radio signal interference. Supernovae and GRBs continue to be crucial for studying cosmic phenomena, including dark matter, dark energy, and the expansion of the universe. These stellar explosions are key to understanding the universe and will remain an essential focus of future astronomy. The Planet 9 hypothesis ignited a wave of scientific inquiry, with astronomers worldwide joining the search for this elusive celestial neighbor. The quest for Planet 9 is fraught with challenges, showcasing the immense scale of the universe and the constraints of our current technology. Its presumed vast and elliptical orbit takes it to the farthest reaches of our solar system, an area where sunlight is almost unreachable, enveloping the planet in total darkness. This isolation presents a significant obstacle, as the potential location of Planet 9 could span vast portions of the sky, requiring extensive detailed searches to cover these celestial expanses. A task akin to finding a needle in a cosmic haystack. Furthermore, due to its distance from the Sun, the planet's surface temperature is extraordinarily low, resulting in minimal thermal radiation and making infrared detection exceedingly difficult. The absence of emitted or reflected light is further complicated by the glare from distant stars and numerous cosmic objects that also occupy the sky, competing for the attention of our telescopes. Adding to the complexity is the planet's immense orbital period, believed to last thousands of years. From our earthly vantage point, the planet's movement across the sky is imperceptibly slow, with its position changing only slightly over the course of a decade, making any short-term observation nearly impossible. This slow movement renders traditional methods of detecting planets, such as observing their transits or motions against the backdrop of stars, ineffective. Nevertheless, astronomers persist in their search, employing an array of sophisticated techniques and instruments. Ground-based telescopes with advanced adaptive optics and space-based observatories that bypass Earth's atmospheric distortions are essential in this endeavor. To enhance the search for Planet 9, astronomers have developed several innovative methods utilizing unique features of the solar system and the potential celestial interactions Planet 9 might have with other objects. One such approach involves exploring the possibility that Planet 9 may have moons orbiting it. Given its considerable mass, it is plausible that the planet could have captured one or more moons during its long journey through the solar system. This idea is based on the process of tidal heating, where the gravitational interactions between a planet and its moon generate internal heat within the moon. This phenomenon is responsible for liquid subsurface oceans on moons like Europa and Enceladus, as well as vigorous volcanic activity on Io. These moons could emit more detectable infrared radiation than the planet itself, providing a promising avenue for detection. Another innovative method involves tracking the paths of interstellar asteroids that pass through our solar system. These high-speed objects, originating from regions outside our solar system, could be influenced by Planet 9's gravitational pull. By meticulously monitoring the trajectories of these asteroids, astronomers can infer the presence and position of a massive planet through the subtle gravitational effects it has on these bodies. This technique was demonstrated through the study of the interstellar asteroid Oumuamua, whose trajectory was slightly altered by an unseen object's gravity. The paths of spacecraft traveling through the outer solar system can also offer critical insights. Similar to asteroids, spacecraft on long journeys experience slight but measurable changes in their trajectories due to the gravitational forces they encounter. By analyzing the detailed tracking data from these missions, scientists can detect anomalies that might hint at the presence of Planet 9. However, this method requires vast amounts of data collected over long periods, as the gravitational effects are incredibly subtle, but the rewards could be substantial. The quest for Planet 9 also spurs intriguing theories about its true nature, suggesting it could be a primordial black hole, or a dense clump of dark matter. The hypothesis that Planet 9 could be a primordial black hole presents a novel idea. Unlike stellar black holes that form from the collapse of massive stars, primordial black holes are theorized to have emerged shortly after the Big Bang. These objects could be as small as an asteroid, but as massive as a planet, potentially explaining the gravitational effects attributed to Planet 9 without the need for a visible planetary body. Alternatively, Planet 9 might be a dense concentration of dark matter. Dark matter, which neither emits, absorbs, nor reflects light, constitutes a significant portion of the universe's total mass. Dark matter clumps are thought to have formed from density fluctuations in the early universe, leading to the creation of structures ranging from small clumps to massive halos around galaxies. If Planet 9 were one such dark matter cluster, its gravitational influence could explain the effects observed in the outer solar system, without being detectable through conventional telescopic methods. The hypotheses of primordial black holes and dark matter clumps underscore the profound implications of the search for Planet 9, which extends beyond merely discovering a new solar system member. Whether it's a planet, a primordial black hole, or a dark matter clump, the discovery would redefine our understanding of the cosmos. The search has led to significant advancements in astronomical techniques, as evidenced by a recent preprint by Mike Brown, Konstantin Badagian, and their colleague Matthew Holman, titled Pan-STARRS: One Search for Planet 9, February 1st, 2024. This study utilized extensive data from the Pan-STARRS-1 survey, which offered a broad and deep sky view, making it an ideal tool for the search. The researchers sifted through billions of detected objects, an endeavor akin to finding a single grain of sand on an entire coastline. Though the search did not uncover Planet 9, it did rule out 78% of the parameter space where the planet could reside, significantly narrowing the focus. Looking forward, the launch of the Vera C. Rubin Observatory promises to usher in a new era of astronomical exploration. With enhanced capabilities to pierce the cosmic veil, this observatory will further the search for Planet 9, continuing humanity's relentless pursuit of knowledge and exploration in the vast, mysterious universe. As Pluto continues its long journey away from the Sun and into the more distant parts of its orbit, dramatic changes are unfolding in its atmosphere. The gases that once thickened the atmosphere are now cooling and condensing, turning into fine snowflakes of nitrogen, methane, and carbon monoxide that fall back to the surface. This cyclical process of sublimation and condensation is a key aspect of Pluto's climate, continuously reshaping its surface over centuries. The varying forms of ice and vapor that evolved throughout Pluto's long year offer a picture of a world in constant motion, far from a frozen static wasteland. Instead, Pluto's surface is dynamic, highlighting the active nature of even the farthest bodies in our solar system. Another fascinating discovery about Pluto's atmosphere is its escape rate. Unlike the larger planets, which have strong magnetic fields and gravitational forces that protect their atmospheres, Pluto's weak gravity allows much of its atmosphere to escape into space. This phenomenon contributes to the ionized gas tail, a faint comet-like trail that Pluto leaves behind as it orbits the Sun. However, this loss is not gradual, but results from interactions with the solar wind, a stream of charged particles emitted by the Sun. These particles collide with the escaping atmospheric gases, creating a constantly shifting environment around Pluto, akin to a small magnetosphere where solar and planetary forces interact. Turning our attention to Pluto's largest moon, Charon, we encounter even more surprising discoveries that challenge our understanding of celestial bodies in the outer solar system. Charon, which orbits in synchronized motion with Pluto, was discovered in 1978, revealing that this moon is much more than a simple satellite. It's a unique world, rich with geological wonders and a history intertwined with Pluto's. As New Horizons flew past Charon, it captured images of vast canyons that could easily engulf parts of Earth's Grand Canyon. These deep chasms tell the story of geologic upheaval, while the mountains rising dramatically from the surface hint at tectonic activity and possible cryovolcanism. The landscape of Charon is a testament to the dynamic history of this distant moon. Charon's synchronized orbit with Pluto means it always shows the same face to its parent planet, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit a common point in space, called the barycenter, lying between the two bodies. This unique relationship challenges the traditional definitions of planets and moons, suggesting a binary system where both Pluto and Charon share equal importance. The gravitational influence of Charon stabilizes Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra, by maintaining a delicate balance in the system. Pluto's position in the Kuiper Belt, a vast region of icy bodies beyond Neptune, offers key insights into the early solar system. The Kuiper Belt, containing objects like Haumea and Makemake, is a frozen archive of our solar system's birth. These objects, including Pluto, are remnants from the time of planetary formation, and their composition of ice and rock offers a glimpse into the materials that once filled the early solar system. Exploring Pluto and its neighbors in the Kuiper Belt enhances our understanding of the solar system's formation, shedding light on the processes that created the planets. The New Horizons mission to Pluto marked a significant milestone, but it didn't stop there. After passing Pluto, the spacecraft continued its journey to Arrokoth, a Kuiper Belt object, where it made another groundbreaking discovery. Arrokoth's unique shape, resembling a snowman, revealed how two primordial objects gently merge in the early solar system. This interaction provided valuable information about the slow processes that shape the outer reaches of our solar system. Looking ahead, scientists and engineers are already brainstorming new missions to explore Pluto and beyond. One potential mission involves an orbiter that would map Pluto's surface with unprecedented detail and study its small moons. By using Charon's gravity to help navigate complex orbits, this mission could offer a comprehensive view of Pluto's system, advancing our exploration of the outer solar system. With advances in propulsion technologies such as fusion drives, future spacecraft could reach distant worlds like Pluto in a fraction of the time it took New Horizons, opening up new frontiers in space exploration. As we move forward in our exploration of the solar system, Pluto's legacy and the discoveries from the Kuiper Belt continue to guide our understanding of the universe. From its dynamic atmosphere to its complex orbital relationships, Pluto challenges our definitions of celestial bodies and reminds us of the vast, interconnected web of forces that govern our solar system. Pluto's interaction with Neptune further complicates its classification. Despite crossing Neptune's orbit during its elliptical journey, the two bodies never collide due to their gravitational resonance. This relationship challenges traditional views of planetary positioning, leading to ongoing debates about Pluto's status as a planet. In 2006, the International Astronomical Union redefined the concept of a planet, resulting in Pluto's reclassification as a dwarf planet. a change that sparked widespread discussion and led to the redefinition of many other celestial bodies. In addition to Pluto, Saturn, with its enigmatic rings and mysterious hexagonal storm, continues to captivate astronomers. The planet's iconic rings, made primarily of water ice, are constantly changing, influenced by Saturn's gravity and interactions with its moons. However, these rings are gradually disappearing due to processes like ring rain and micrometeoroid bombardment. Saturn's storms, particularly the hexagonal vortex at its north pole, challenge our understanding of planetary dynamics, offering a striking contrast to Earth's more chaotic weather systems. Saturn's moons, such as Titan and Enceladus, have also sparked debates about the potential for life beyond Earth. Titan's lakes of liquid methane and Enceladus' geysers of water and organic material make these moons fascinating subjects of study in the search for life in the universe. Saturn, with its complex systems of rings and moons, serves as a reminder of the mysteries that remain in the outer reaches of our solar system. Titan, Saturn's largest moon, is a world full of enigma. Its thick atmosphere contains abundant organic compounds, and its surface hosts rivers and lakes of liquid methane. Yet, what truly stands out is Titan's astonishing movement away from Saturn, occurring at a pace 100 times faster than previously estimated, at a striking 4.3 centimeters per year. This rapid drift hints at a dynamic and ever-changing relationship between Titan and Saturn. Could this shifting affect Titan's internal dynamics, and possibly even its potential to harbor life? Titan's atmosphere, rich in organic materials like nitrogen and methane, along with the possibility of an underground ocean, makes it an enticing target in the search for extraterrestrial life. However, the question remains, what would life look like in such a vastly different environment from Earth's? Let's not forget Enceladus, another of Saturn's moons which is quite unlike Titan. Enceladus is an icy moon, with a surface so reflective it shines brighter than any other body in the solar system. Enceladus pushes the idea of an ocean world even further, as it has a subsurface ocean that actually erupts into space in geysers, offering the chance for space probes to collect samples. This ocean contains all the chemical building blocks necessary for life, including hot, mineral-rich water vented from hydrothermal vents, similar to the extreme conditions where life thrives on Earth. Could these vents harbor similar yet alien life forms? Enceladus also contributes to Saturn's unique E-ring, a complex system that enriches the understanding of the moon's relationship with its planet, offering a glimpse into its internal chemistry. Titan and Enceladus, though both moons of Saturn, differ vastly in their environments, yet both present intriguing possibilities for life beyond Earth. Our curiosity about the potential for life on these moons goes beyond telescopes and computer models. Future missions will allow for direct exploration. For example, NASA's Dragonfly mission, set to launch in the 2030s, will fly over Titan's varied terrain, from dunes to craters, to search for the basic building blocks of life. It will analyze Titan's complex organic compounds and gather data on the moon's chemistry to help us understand its geological processes and how they might relate to the potential for life. Could Titan's chemical makeup and methane cycle offer a completely different form of life? Although no missions to Enceladus are currently underway, the moon's potential for life continues to attract interest. Proposed missions may fly through Enceladus's geysers, collecting samples from its subsurface ocean. Studying these samples could provide critical insights into prebiotic chemistry, or even direct evidence of extraterrestrial life, given that Enceladus's hydrothermal vents offer an environment capable of sustaining life. Shifting to Saturn's iconic rings, recent findings show that they're not as permanent as we once believed. A process known as ring rain is slowly causing these icy wonders to fade, significantly affecting Saturn's atmosphere. Research by the Japan Aerospace Exploration Agency reveals that ring rain, which carries away water equal to the volume of an Olympic-sized swimming pool every half hour, lowers the electron density in Saturn's atmosphere, influencing its overall conditions. Interestingly, despite Saturn's age of about 4.6 billion years, the rings might only be a few hundred million years old, suggesting they could have formed from the destruction of a moon, or the capture of a passing comet. NASA's Cassini mission provided additional complexities, revealing that the rings appear surprisingly clean. Over its 13 years in orbit, the Cassini Space Dust Analyzer collected 163 dust particles from outside the Saturn system, leading scientists to question why the rings, considered young, haven't accumulated more cosmic dust. This cleanliness challenges our understanding of the rings' age and their interaction with the broader cosmic environment. As Saturn's rings slowly dissipate, the planet's appearance will dramatically change, potentially affecting its atmospheric dynamics. The disappearance could alter Saturn's wind patterns, affect its heat retention, and even impact its iconic storms. This loss could have cascading effects on the planet's atmospheric system, making the rings' eventual vanishing a topic of intense scientific study. Additionally, Saturn's rings may be linked to its moons, as some theories suggest that gravitational instability may have destroyed some of its icy moons, providing the material for the rings. These satellites and rings interact in a cosmic dance, each influencing the other in subtle yet significant ways, revealing new insights into the nature of this planetary system.